everyone. Let's see how this goes because the Godot console sports launch was this week, and that took all of my time because I've been doing that since last year and barely had enough time to get through this in the same way. So fingers crossed that will work and everything. Let's see. All right. So, hi, I'm Shana. I help out indie devs port their games. I also work on game engines. That's why I'm working on the Godot console port. I used to work at Unity on the game engine. I used to work at GitHub with GitHub for Unity and GitHub for Visual Studio. I've ported a bunch of games, and I worked on the Mono project on Mono. So we're be talking about embedding C# right now, and it's a thing that I've been doing for a really long time, and it doesn't really get any easier with time. So my hope with this talk is that it is a bit easier for you to do this, and I have tried to document how to do it in a cross-platform way. And hopefully you can replicate and do this, which is a fun thing, running C# on your C++ app. So let's do this and hope for the best. All right. So why? Why C#? So why would we want to embed C# on a game engine or an C++ app, to be honest? So you can run other scripting languages, you can do a lot of things. But the reason why one would want to embed a scripting language in the C++ environment is because every language exists and doesn't exist in a vacuum. Every language has its own uses, its own like things that it does best. And C# is a particularly expressive and powerful and performant language that people without an engineering background can easily get into. It can be used for scripting, for programming. It kind of combines uh, the values of performance and ease of use in a way that not a lot of languages do. You can also embed Lua, you can embed Python, you can embed all sorts of languages. They will always be embedded for that purpose, to provide a quick and easy tool for someone to quickly script behaviors without worrying about memory pointers and C++ and whatever. C#, I think, is more powerful than most other languages out there for scripting. It can live in a lot of environments that other languages don't perform well at. So that's my excuse for this. I've also been doing C# since 2005, so I'm biased. What can I say? So how to embed C# is a complicated problem because there's a lot of words and concepts involved. And if I just throw you the code or the concept, like if I start explaining this stuff technically, it will make no sense. It might make sense for some of you, probably not all of you. There's too much jargon, too many words. So before we start on the technical things, we're going to go through the words and try to make sense of what the vocabulary for C# and embedding environments is, so that we can make sense of the technical parts. And so let's start with the story, because just throwing a bunch of words doesn't make not fun. Not fun. Let's get a story going, and let's start with Java, because why not? So Java appeared in the world 1997, 1995. It exploded in the world, not necessarily appeared then, but it exploded in the world, and it was all the rage back then. In 96, I think it was when we came in. And they came in with a really, really nice, catchy tagline, which was write once, debug everywhere. Sorry, run everywhere, anywhere, run anywhere. That's it. Got it wrong. It's fine. Java, write once, run anywhere. And the reason for that is because Java, instead of being a normal language where you write some code and it gets compiled, uh, into the machine code that is going to run on that machine architecture, Java introduced the concept of a virtual machine that abstracts away the particulars, specifics, and differences of the actual machine that your code is going to run into. So the virtual machine is a little sandbox inside the OS, hiding away all the specifics. And Java targets that virtual machine, and the virtual machine executes. And the virtual machine's job is to do the actual native things that that particular machine needs to. And it does this by Java creating a bytecode that's standardized for the virtual machine, so that when you write your code, that code gets compiled to bytecode, the virtual machine executes it. And now which OS and hardware that virtual machine is going to run to is no longer typically your concern. It is whoever implements the virtual machine implementation for a specific OS, for specific hardware, will implement that, but your code is going to be running on a virtual machine, and it doesn't really matter where that virtual machine is. And so you don't have to worry about the details of the assembly code needed to run on this machine, or what a network call looks like on this machine, or what the file system looks like. You write it once, and it runs, which is where the run once, write once, run anywhere comes from, but also write once, debug everywhere, because turns out it's kind of hard to make an abstract virtual machine that runs anywhere. But it was a super, super, super powerful concept for a time where all languages are either just interpreted or assembly code. And with barely levels on top of something that was more abstracted and easy to get into, but really still hard. Like programming is very, very, very hard to do, because all of the languages that were powerful enough to do it were just very complex, and still are, a lot of them. So this is super hot idea. Everybody was on this board, including Microsoft. Microsoft is super excited about this because they had a really big problem. They needed to expand their developer market. They want more developers to build apps for Windows, but like programming for Win32 is something. Win32 APIs, COM APIs, C and C++. It was really, really hard for people to make apps that were secure, that ran without crashing all the time, like all of the problems of creating native apps in C and C++. And they wanted a easier way to give tools to people to create apps. And Java came in with this idea where, hey, we can just have a simpler language that just hides away all this complexity. It was great, portable, perfect. The problem was native calls. So in order for Java to be performant on Windows, because Windows is all Win32 native APIs, Java needed really, really, really performant in native calls. It would just have to be fast. Otherwise, an app written in Java running on Windows would be super slow. And the problem was Java was never meant to run like this. It was never meant to allow you to call the operating system directly. It's always meant to run on specialized Java hardware. There was even Java machines. It was always meant to run on a virtual machine and hide everything for you. So this was a problem for Microsoft. And so they decided to do something about it. And this is our first concept, first couple of word clouds. So now we're going to be putting up some word clouds together here. So we have native calls is kind of a key thing here, which is where the ability to be able to call a API, a function that is written in another language, C, C++ usually, and in a performant way. So Microsoft's solution to this was to create Visual J++, which is basically the fastest VM Java implementation by far, because Microsoft kind of knows how to do this. So they were better at it than everybody else, um, with some extra features on top, which is the fast native calls. And so what they did was for Java, it's literally just Java, and then they added some extra syntax in form of a comment when you call a function that's supposed to be a native function of a thing that was implemented in a library written in C, and you put a little comment on top of the signature, the declaration of the signature that you're going to call, saying which library where this thing should be called into. And the Java VM, the Visual J++ VM implemented by Microsoft would interpret this, and bypass the garbage collector, bypass everything, and just go straight down to C. This is the JDirect, an example of a JDirect call from 96. And if you notice, and if you've done this sort of thing in C# before, you might find this syntax strangely familiar, because this is the C# invoke call. And I will actually put them side by side so that you can compare how this evolved, where this came from, basically. So this was all fun, and this is all fun. July, August 96, everybody was raving about this. And then and then by 97, Microsoft's getting sued by Sun. And the funniest bit of the articles around this time is that their complaint, the major complaint that ended up triggering the massive antitrust lawsuit that ended up forcing Microsoft to take out Internet Explorer from your desktop, is because Sun was very annoyed that Microsoft has added functions on top of their API. So they didn't change Java, they just added a couple 50 methods on top of it. And that is highly offensive, extending the Java libraries with 50 methods. And this is specifically in the complaint. And there's a bunch of keywords here that that are relevant to our conversation, that we're going to put on our word cloud, which is native calls and class libraries. Class library concept comes, that you might or might not have heard from C#, is the set of libraries that are made available as part of the language itself. And that set of libraries is called class libraries because they're available as part of the language. And usually, like, they don't change that much. You can rely on them. And that comes from Java, and we have those in C#. And native calls is the other concept that we have. It's the eternal struggle of the native calls. So we can't have J++ because we have a lawsuit, and we're getting sued by the American government over adding things to a library. So let's not call it J++. Let's call it C#. Might as well. Like, just make a new language, which is the same language, but with a different name. Might as well improve on some things, but I mean, not change that much because it already had the thing. The interesting part of all of this is that Java was never open source. It was never standardized. It was never open source. They got sued specifically because the license agreement for Sun and Java did not allow anyone to extend the library, to implement VMs, to do anything other than use the thing that was there. And so they decided to do C#, but in an open source way. So it was just open source up front, open standard, standardized. This is what it is, as a proof of good intentions, I guess. So it's just highly ironic. So now we have C#. And let's go back to our virtual machine bytecode Java thing and put in C# instead, because we're still in the same model. This is what C# is. The compiler produces bytecode, and then the virtual machine is executed. If we expand this more, we have the native calls at the bottom. The virtual machine will do the native calls into the OS, depending on what it needs to do, those native calls that are super, super important to be very, 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 very fast. If we expand this a bit more and we introduce a couple more concepts here, the virtual machine is the common language runtime, as it's called on the C# land, and it's composed of either an interpreter or the just-in-time compiler, depending on what type of mode the virtual machine is running in. It has an exception handling service. It has type safety, garbage collector, thread management. So it's kind of like a little OS inside the OS, doing its thing and then calling out into the actual real world OS. And then the OS calls back into C#, et cetera, et cetera. Those go into our little bag of words. So we have the common language runtime, the interpreter, and just-in-time compiler. A few more words going in here. We're starting to get a lot of words, so get these into acronyms. CLR is what we call the runtime. GC for garbage collector. JIT is the just-in-time compiler. Interpreter, we still call it interpreter. The bytecode we call IL because it's an intermediate language representation. It's what it's called, and it's basically literally what it says in the tin. It's an intermediate language. It's not exactly what the thing is actually going to run natively in the end, but it is not C#. It's at middle level. It's a standard that looks like assembly, but it is not assembly. So all of this is called .NET Framework, or was called the .NET Framework back when it came out. At which point we need to talk about naming conventions for .NET, because this is going to be starting to be very complicated if I start saying .NET 10 times and it means 10 different things. And Microsoft's just so good at naming things that we need to talk about this. Initially, .NET, it was the ecosystem, the brand, .NET. .NET Framework, the actual language, tools, the class libraries, the runtime, that was a thing. And when we talked about .NET, we were talking about the whole overall thing. .NET Framework, that specific version of the thing that we were using, is what we were doing. And it's been around for 20 years, finally stopped being updated. So that's nice. And for .NET Framework, kind of important, hopefully less important as we go forward, we have versions 1 to 4.8.1 of .NET Framework. As I said, it's based on public standards. The languages are available. You can download them. You can see them. The standard for the language has been updated. It's constantly being updated, but the infrastructure, the IL and everything, surprisingly, it's stopped since 2012. It hasn't been needed to update it, which means the runtime basically has all the needed features for any future feature, current or future feature that C# actually has. The runtime already supports it. Anything that's been done in C# these days is just, syntactic sugar, like changing syntax, but the runtime can already run everything, which is important to us because that means anything that's compiled today, a runtime from 10 years ago can run, which is interesting if you imagine compile something, create a DLL with a .NET Core compiler version, language 9, 10, whatever, and you can run it on Mono from 10 years ago, and it will run because the VM, the CLR, the IL standard hasn't changed. All the features are there, and so it can run. which is really super interesting when you're wanting to build a thing on one version of the .NET Framework, .NET Core, and then run it on a different one. It also comes with patent promises, which is super important. That means that anything that's implemented that might be covered by a patent in the implementation of this stuff is this patents will not be enforced. You're fine, you'll never get sued for them, which is the whole problem with Sun. So that's burned, kind of like being different for Microsoft, trying to be better. So at some point in 2016, they decided that .NET was too meh, and let's call ourselves .NET Core and do a cleanup. There's a lot of APIs that really needed to be cleaned up, and you really can't throw away the class libraries that are backwards compatible and everything if you don't clean up house. And so cleanup was needed, and they decided .NET Core and .NET Core 1.0, but not the language version, because the language version is based on the standard, and the standard they can't reset that. So now the language version of C# and the .NET version became out of sync. But that's fine. Okay, that's okay. .NET Core 1.0 to 3.1, we're good. And then .NET Core 4 was about to happen, and they realized people were, when they're running code, embedded code, they were looking for the framework, the version that was stamped into the DLL, saying which .NET version it had been compiled against or run against, or it was running against. And if it was .NET 4, do X. Of course, they weren't checking whether it was .NET 4 or .NET Core 4. So that was a problem. Turns out their tooling did that too, to kind of go like, oh, we're in .NET Framework 4, do something else. So that's okay. Let's skip .NET Core 4. It's fine. It's not a problem. We got this. But I mean, if we're skipping .NET Core 4, might as well rebrand the whole thing, because like this is still not like, we don't really like this. .NET Core kind of weird. And let's call it, what are we gonna call it? .com? That's silly. Maybe .NET. Let's call it .NET. But the problem is the command line tool. So like there's a CL, that's the compiler, Mono has its own compilers, like there's all these different toolings, and we really, really need to have like a uniform standardized thing. Let's rename everything. Let's just really do a good renaming in here. Let's call it .NET. So now .NET is the ecosystem, .NET is the tooling, and .NET is the command line. Okay, clear? Easy to follow. It's fine. Don't have to remember anything. Everything is .NET. This is not up to date because there's more versions now, but this is the thing. When a Visual Studio says this feature is not available in the C# version, it's not complaining about the .NET or .NET Core, the .NET Framework or .NET Core version. It's complaining about the C# specific language. But all of these target different. It's a mess. It's a mess. I don't like this. I can't talk about this if everything is .NET. So when I say .NET, it's the ecosystem. It's the thing. It's the whole bundle. When I say .NET Core, it's the tooling and CLR and class libraries. Especially because the runtime is called, literally the DLL is called Core CLR. So it's .NET Core. It's core. And I'm going to say the .NET tool. Well, what else can we say? It's called .NET. And I can't say a dot instead of dot. It's very confusing, but I will say the .NET tool, and hopefully it's not going to be confusing during this talk. Your mileage may vary afterwards. So word cloud, we got ourselves the .NET tool, .NET Core into the mix. We got ourselves some p-invokes, compilers, C-sharps, tools, class libraries, all of the nice words. This is .NET. So going back to our little picture of what's happening between the C#, the virtual machine, and native calls. We saw before that C# turns to bytecode, virtual machine executed, and then OS calls happen because the virtual machine needs to call down to the native to do actual like things on the OS. Let's turn this sideways, because our goal here for this talk is embedding C# in a C++ application, which means our entry point is C++. So we're going to come in from the left side of this chart. We start up our app or game, whatever. Like this can be a game engine, C# embedding, it can be app, it doesn't really matter. It's all the same. We start with C++ land, and at some point in C++, we initialize the CLR, the runtime, and we tell it, go please run me this code. And the runtime will start up and run C#. It will load the DLL from disk. It will interpret and start reading the IL that's in the file and start interpreting or running the JIT over it, which is a just-in-time compiler. So it literally, as it's interpreting the intermediate language, it is compiling it at the same time to machine code. So the next time that code runs, it now runs full machine code. It doesn't have to interpret the IL again. So that's a just-in-time compiler. It will run the GC, etc. And at some point, managed side is going to scale. Oh, I need to call this C method or C++ method. And the CLR is going to call back into us, if that's what the C# is calling in back into us. So that's the loop. We start on the left side, and then it goes back and forth data between these lands. And this is another two things that we want to make sure we are clear. The C++ side is called the native land, and the C# side, VM, CLR, everybody, is called managed land. And managed land is a term that's used very commonly to describe everything that happens on that side of this fence. And you might hear terms like native peer, managed peer, which are like objects that are like linked together. So if one of them is garbage collector, dies, or destroyed, the equivalent on the other side is also destroyed, and which is very common in game engines, in Unity. Definitely. So these two native and managed lands are like where we're going to be living. So the calls back from C# from managed land into native land is called a p-invoke. I can't even remember what platform invoke. It's a platform invocation. That's why it's called p-invoke. So p-invokes are, there's many ways of doing them, but there's generally, if you're going from managed to native, it's a p-invoke. If you're going to native and managed, it's just running C# code. There's no word for it. So C# as an embedded language started, I'm sorry, I think I ran out of. Can you hear me? Yeah, I ran out of battery on my headphones. Sorry about that.
We can still hear you and see you, so everything's still okay.
Okay, give me a second here because. All right. Okay, sorry about that. I ran out of battery on my headphones. It didn't even tell me. All right, so C# as an embedded language started with the Mono project because the Mono project was an implementation of .NET, the language, the compiler, everything on Linux. And for ease of use in general, just to make that thing, just re-implement the whole thing, it was just much easier to start from C and C++ than to start as a pure C# environment, especially because Linux runs on so many things. It was just like the way that it uh, got created just lent itself to being a very small embeddable engine that you could just put somewhere and run. So much easier to test too. Um, and so Mono Project's first released in 2004, and it was basically just reading the standards and implementing the thing. And cross-platform, because we kind of had to run this on Windows to be able to test, because you're implementing a thing, like you're bootstrapping your own thing. It's kind of hard to build a compiler for a language when you can't compile the language, so you need to build. It's chicken and egg thing. So it ran on Windows and Linux and Mac, just because everything's Unix in the end, and open source. And for a treat, it came with an ahead of time compiler, which we're going to shove into our little word cloud here. So AOT is the third mode of execution. We have the interpreter, where it just goes through one by one of the intermediate language and executes it. We have the JIT, which goes through and compiles it as executing. And AOT, where it's literally compiling to native code the IL before it's executing. So doing what the JIT does, but ahead of time. This is so that in environments where the JIT can't execute because memory can't be written to or whatever, you can pre-generate the machine code for that architecture ahead of time. That's why it's called ahead of time compiler. So mono's used everywhere, acquired. I'm going to skip through the history lesson here. I'm mostly have these slides for reference so that you can later see the slides. Just going to briefly mention that Unity leveraged the C# mono compiler and runtime to be able to put C# in games. And embedding mono until at least in 2011, when everybody got fired. And then the license just went up in smoke. And Xamarin was created, which took the IP from Novell and ran with the mono projects and gave license to everyone. So we can still embed C#, except Unity. Unity didn't get a license. This is where IL to CPP exists because of this licensing problem. So Unity had two problems. They couldn't run GPL. The mono open source license was GPL. Then Apple didn't like that. Mono had a commercial license, was not GPL, but Unity didn't have one of that after 2011. So Unity decided to create IL to CPP, which is basically taking the intermediate language, instead of running the runtime with it, it transforms it into C++, which can then be compiled with a normal C++ compiler, and then it's no longer running in that VM, which is licensed badly, and they can do their game engine. So this is what Unity looks like. It's an extra step at compilation time to execute the C#. So, and then everything went open source, and Xamarin got acquired by Microsoft, which is really nice because Mono now lives in the .NET Runtime repo, which is going to be handy for us right now as we're going to be looking into how to embed this thing. .NET also went open source, but I mean, it was not made to be embedded, so it's never very useful for embedding. The advantage of having Mono and the Mono team working with the same team as .NET Core is that their embedding capabilities slowly propagated into the Core CLR, and actually added embedding capabilities into the Core CLR. So now everything is .NET, Mono is .NET, .NET Core is .NET, everybody's .NET. So let's talk about actual embedding. So we have two runtimes. We have Mono and Core CLR. They all run in Mono runs everywhere, basically. Core CLR runs on desktops and on some other platforms, depending on some other platforms. Maybe iOS. There's experimental previews. Maybe not now anymore experimental, but there's a subset of platforms where Core CLR runs. Mono has three modes: JIT, interpreter, and AOT. Core CLR has two. They never built an interpreter. The interpreter that they have is only for testing, and it's not actually good for production. And which one do we use? How do we choose? We use all of them. All of them. Because it really depends on which platform you're going to be trying to run C# on and what tooling exists for it. So if it's Win, Mac, and Linux, you can use any modes. All of them are available. If it's iOS, you need to use an interpreter or EOT. You cannot use JIT on that platform. And there's no Core CLR interpreters. So there you can only use AOT. For Mono, you can use either. Android, you can use all of them, but you either do interpreter or AOT because JIT is super heavy at runtime, and you probably just don't want that. On the web, AOT or a JIT interpreter. WebAssembly, there's a lot of like retranspolations of IL for web. And then on consoles, you can only use AOT interpreters, the same restrictions in iOS. You're not allowed to JIT. So let's look at actual code. The basic embedding steps for embedding C# is you're on your C++ app and you call something to initialize the runtime, whichever runtime it is. It could be Mono, it could be Core CLR. Once the runtime is initialized, you can call C# methods and C# can call you. And basically that's it. And now you're passing around data as arguments and return values, and you're good. Because we have all of these combinations of setups, mostly we have like three broad setup types, which is AOT is not a runtime, but for the purposes of this, because the tooling is so different, it kind of is. And like the initialization of the AOT mode is just so different. You can almost think of it as a different runtime to initialize. So we've got Mono, and it doesn't really matter which mode it's just a flag to tell it which mode you want, Core CLR or AOT. For both runtimes expose a C API to do the setup. Mono is an extensive API. You can really control the runtime and do everything that you want. Core CLI is bare minimum, but because Mono's living in .NET runtime and Xamarin Mono for Android, Xamarin Android needs a lot of control, and Xamarin for iOS as well needs a lot of control over how the runtime is initialized. Some of these APIs, like some of these embedding capabilities, have been slowly trickling into Core CLR, so we actually have more stuff in there that we did before. Also, you don't have to compile Mono or Core CLR or any of it from source to embed C#, because all of the packages for the runtimes are available, and you can just reference them with NuGet and grab them and start using them directly. Also, another advantage, like this came out of the fact that Mono runs on all of these environments, so it's kind of handy for their tooling to have the Xamarin tooling to have access to all this stuff, and so over time, this stuff became available. The Core CLR initialization is on Windows is horrible because it makes assumptions that why would you ever embed anything? Terrible, horrible. It's convoluted and really annoying. The Core CLR non-Windows is one call, Core CLR initialize. Done. No OSFXR, no nothing, just done. For Mono, there's a bunch of different calls that you have to do in order for actually getting the setup to go. And this is where we start talking about CSharpify, which is a little project that I put together that takes care of all this stuff, because just taking care of all this stuff is just so much really annoying work of trying to figure out what each runtime is doing, that I got tired of it and put it all together in one thing. So that's the URL. It's also where a version of these slides is. And that's what we're going to be looking at it today. It's a header and source and CMake library that you can just consume as source, and has like, just load the runtime. Okay, thanks, bye. But also has a little example of how to embed C# in a game engine by taking a DRM GUI, which is a GUI library, C GUI library that has a bunch of examples, and just plugging C# into it so that we have a nice window. So the way to do, once you have initialized this, and I promise we'll get to an example 2 minutes. Once you have initialized your runtime, the next thing you need to do is to call a C# method. To call a C# method from the native side, you need a pointer to it. You need to ask the runtime to give you a pointer that you can use to call it. And you do that with core CLR create delegate, where you give it the handle of the runtime that you've initialized, and then you give it the name of the assembly, the type, and the method that you want to call, and it'll give you back a little function pointer, a delegate. Delegate is the word that you've probably seen if you do any C#, which is literally just means a thing that you can execute that represents some function, but it wasn't, it wasn't determined at compile time. You create it at runtime, and that thing points to that function that you want to call. Goes into our word cloud. On Mono and on Windows, core CLR doesn't even need domain IDs. You just call a little pointer. It doesn't use it. It can just go. So this is what the code for running on C# and C++ code for calling a method would look like. On C#, you would have, imagine you want to call from C++ to C#. You want to call a method. And so you declare it on C#. In this case, it's a static method because that's the easiest version of this. It's a static method called isOK that returns false on the C# side. You have a attribute called unmanaged callers only, which tells the runtime when it's compiling, tells the compiler when it's compiling, don't throw this away, even though nobody's using it, because this is going to be called from the native side. That's important because the compiler will trim anything that's not getting used. There's no point in compiling it. If this isn't used on the C# side, it'll get thrown away. So that's what that attribute is for. On the native side, the C++ side, you have a declaration, C++ declaration of the function, which is a static bool, returns bool, and doesn't take any parameters. And then at some point in your code, you're going to call core CLR create delegate, and it will return you that function pointer, and you just call it. The types that are returned, the data that is returned, this is an important little detail. You can only move data around that's splittable, and by splittable it means it can be copied from C# to C++, or at least represented from one side to the other. It's a chunk of memory that one side and the other agree that it represents that. The unmanaged callers only attribute also makes sure that the types that you're calling, like using for your calls, match, are splittable and can be passed around. So some more words for our word called trimming and splittable. So you want to go from C# to C++. It's our friend DLL import that we saw at the beginning. And you tell it which library you want to call. And in this case, it's the name of your native executable library, or magic names that we will see in a bit. And you declare that as a static extern. Extern is important because it's an external. It's not, there's no implementation of it on C#. And then when you call it, it goes here into our isOK. So in practice, let's look at this in practice. In practice for CSharpify, I have CSharpify here. In practice, what this means is that this call here, like this is the entry point to my C++ app. It's going to come over here and call our onStart method. And I'm going to put a little breakpoint right there. And I'm going to be, I don't have, let's put a little breakpoint right there. So this is our C# unmanaged callers only. It's a static void. Visibility doesn't matter. And this is our C#. And that's our C++. Oof. So this is our C# call. And you can see, let me get, oh, I probably didn't compile. I moved code to run and didn't compile, so my breakpoint didn't hit. But we started here on our little native side and called onStart, which is somewhere over here. This gets the pointer from the core CLR that in CSharpify is a little function implemented there that does the same thing as core CLR create delegate, because the signature is slightly different depending on the runtime, so this hides that and grabs the method from the assembly and then calls it. And this is where we are. We are here and we are getting called. And then when we continue, we have my cool window, which is the IMGUI C++ app running on my little app. And then, but on C#, I'm initializing that little window and I'm doing some text. And then I am calling a method here that is our DLL import that we saw before. And this is going into, this DLL import is going into magic name internal, which will redirect our calls into our own running app, because that's what we want to do. We want to call ourselves on the native side. And it's going to call the native method called returning bool. This native method called returning bool is declared here. And if I won't, the breakpoint won't hit because I didn't compile this one briefly, but this one is returning false, and this goes back to C# and gets shown. So the DLL import pinvoke, you can only call C functions because C functions are, the names are known. C++ names are not known. And this is what we're doing, is just calling the pinvoke. So now there's two ways of doing pinvokes. You can do it with DLL import, or we can do it with library import. I have, this code is available for you to look at. I have all of the examples of different ways of doing DLL import and library import with and without bool marshalling. I'm actually running out of time, unfortunately. So, and there's so many more cute examples to show. I just want to give you one question for the audience. You can look at the comments. Does that code run? If it is a method called check if okay, it is calling if okay right here. This is a native call that's going back into C++, and C++ is just returning false. So if this is false, does fail run? This fail run? We don't have a lot of time. So Maybe. Let's look at our code because the code is actually running. So we can look at it. Um, so I'm going to run this again. And our code that we were looking at is this is calling the bool. Bool is returning false. Should be false, but it is true. If you learn anything from this one talk, is that sizes matter. When this bool in C++ is 1 byte, 8 bits, bool in C# is a full 32 bits. So when C++ returns false, it returns 8 bits of false. But when C# reads the bool on the C# side, it reads full 32 bits. Now, it reads whatever memory is in there. So if, there's other parts of the memory that have ones in it, it is no longer false. It is true. So never use naked bools to pass information around because it won't. It just won't work. And so there's this example. We have all of the different ways of marshalling a bool, custom marshalling, and automatic marshalling. The one more thing that I want to leave you with, and you can just look at the code. I will give you the URL again so you can see all of this, is that the way that the magic that is happening here in order for you to just say, call this thing, and it gets called, is with a little package called the DNNE, which is actually a Microsoft internal project that they use for testing, which auto-generates C++ calls and C definitions from C#, which is the thing that makes all of these things so easy to do. So it will generate all of these calls, all of these signatures on the C side based on what you have on the C# side. And so you can quickly and easily just add things on the C# side and it will automatically show up. And so we have 5 minutes to 5. I want to leave some room for questions. Where am I? So all of these slides, and I'll put up another version of these, the updated version of these slides are on the CSharpify repo. And all of the code is in there. And just ping me because there's a lot in here that I did not cover. And if you want to know more, you can go and look at it.